So in the last video, I introduced Taylor series, or I guess more specifically Taylor polynomials, and we learned how to calculate 0 degree, first degree, second degree, and third degree Taylor polynomials that best fit a given function, f of x equals the natural log of x plus 2. And what I tried to do in those videos is give kind of an intuitive understanding of what we're doing when we calculate, for example, a third degree Taylor polynomial. My goal was not to come up with this answer as quickly or efficiently as possible, but instead to kind of get you to understand why we're doing the steps that we're doing to come up with this polynomial. What I want to do in this video is look more for patterns and formulas and stuff that hopefully will make sense based on the work that we did in the previous video that will allow you to come up with these answers a little bit more quickly. Let's pick on a third degree Taylor polynomial, although I think you'll see that this logic holds for any degree polynomial. A general third degree polynomial is some number, I'm going to call it C3, times x cubed, plus some number, C2, times x squared, plus some number, C1, times x, plus some number, C0. We wanted the height of this polynomial to be the same as the height of the function, so we had to consider T3 of 0. But a nice thing about polynomials is when you change all the x's into zeros, a lot of terms go away, and you just get C0. So in order for the height of the polynomial to be the same as the height of the function when x equals 0, we needed this constant term, C0, to be the same as the height of the function at 0. In this specific case, the function was the natural log of x plus 2, so the height of the function at 0 was the natural log of 2. But I want to keep this a little bit more general. I want to give you formulas that work for any function, not just the function f of x equals the natural log of x plus 2. So what we'll need to have happen is have C0, the constant term in our polynomial, to be equal to f of 0. But as we saw, it's not enough to just have the function and the polynomial have the same height at x equals 0. We also want them to have the same first derivative as at x equals 0. So we calculate the first derivative of T3 of x. Maybe I can move stuff around a little bit so it makes more sense. The first derivative of T3 of x, as we saw, is 3c3x squared plus 2c2x plus c1. But really, it's not the first derivative of the polynomial at x that we're interested in. It's the first derivative of the polynomial at 0 that we're interested in. And it's awesome that all these terms except for 1 have x's in them, because when I change all the x's into zeros, they all go away, and I get t prime of 3 when x equals 0 is just equal to c1. So c1 needs to be the same as the first derivative of my function at 0. And then when I calculate the second derivative, I get 6c3x plus 2c2. But really, it's the second derivative at 0 that I'm interested in. And conveniently, again, all of the terms except for 1 have an x in them. So all of those other terms, just 1 in this case, go away. And I get 2c2. So in order for the second derivative to be the same, 2c2 has to be the same as the second derivative of my function, whatever that function ends up being, evaluated at 0. And then finally, the third derivative of my function, T3 of x, is 6c3. Technically, it's not the third derivative of the polynomial at x that I want. It's the third derivative of the polynomial at 0 that I want. But the third derivative is just a constant term, so the third derivative at x is the same as the third derivative at 0, 6c3. That 6c3 is what I need to be equal to the third derivative of my function f, evaluated at x equals 0. It would be nice if c0 was just f of 0, and c1 was f prime of 0, and c2 was f double prime of 0, and c3 was f triple prime of 0, but it's not. We get this 1, and then this 1, and then this 2, and then this 6. It would be nice if there was some sort of pattern going on here, if we could predict all of these different values, because then we wouldn't have to take these derivatives over and over again. And we can predict those values. I'm kind of telling you the pattern down here. 0 factorial is defined to be equal to 1. 1 factorial is defined to be equal to 1. 2 factorial is defined to be equal to 2. And 3 factorial is defined to be equal to 6. And in case you're uncomfortable with this notation, this exclamation point, which means factorial, 4 factorial, for example, is defined to be 4 times 3 times 2 times 1. In other words, 24. So that's where this 6 comes from. 3 factorial is 3 times 2 times 1, which gives me this 6. Oh, right, 2 times 1 gives me 2, and then 1 is just equal to 1, and 0 factorial is a little bit weird, but it makes sense to define it as 1 for reasons that we won't even talk about in this video. The fact that the numbers out in front of these coefficients are predictable is really nice, because that allows us to come up with these formulas for the different coefficients in our Taylor polynomials. Regardless of the degree of the Taylor polynomial, whether it's a first degree, third degree, or 400th degree, the constant term in that polynomial will always be equal to the function that we're trying to approximate, evaluated at 0, divided by 0 factorial. Remember, 0 factorial is just equal to 1. Oh yeah, that makes sense. If I have a 100th degree polynomial, I want the height of that polynomial to be the same as the height of the function when x equals 0. So I change all the x's into zeros. All I'm left with is just c0. That c0 should be the same as the height of the function evaluated at 0, divided by 1 if you want to really come up with a pattern in these formulas. Anyways, if you had all of these memorized and you were trying to redo this problem and you knew that f of x was equal to the natural log of x plus 2, maybe you'd look at these formulas and be like, well, I need f of 0, f prime of 0, f double prime of 0, and f triple prime of 0. So let's start taking some derivatives. The derivative of the natural log of x plus 2 is 1 over x plus 2. The second derivative of the natural log of x plus 2 is the derivative of 1 over x plus 2, which is negative 1 divided by x plus 2 squared, as we worked out in the previous videos. For the third derivative of this function, f of x equals the natural log of x plus 2, I just take the derivative of the second derivative, and as you may recall from the previous video, that ends up being equal to positive 2 divided by x plus 2 cubed. I got the first three derivatives of my function f of x. But really, if you look at these formulas, it's not f of x or f prime of x or f double prime of x or f triple prime of x I'm interested in. It's f of 0 and f prime of 0 and f double prime of 0 and f triple prime of 0. So what I need to do is evaluate each of these at 0. F of 0 would be the natural log of 0 plus 2. In other words, the natural log of 2. F prime of 0 would be 1 divided by 0 plus 2. In other words, a half. F double prime of 0 would be negative 1 divided by x plus 2 squared. In other words, negative 1 divided by 2 squared. In other words, negative 1/4. And finally, f triple prime of 0 would be equal to 2 divided by 0 plus 2 cubed. So 2 divided by 8. In other words, positive 1/4. Now that I have these four values, it's pretty easy to figure out the coefficients of my third degree Taylor polynomial. If I want to know what C0 is equal to, I remember that C0 is f of 0 divided by 0 factorial. So now I know f of 0. I just take the natural log of 2 and divide it by 0 factorial. 0 factorial is equal to 1. So I get the natural log of 2 divided by 1, which is just the natural log of 2. Similarly, I can calculate C1 by taking f prime of 0, which remember is 1/2, and dividing that by 1 factorial. Well, 1 factorial is just equal to 1, and 1/2 divided by 1 is just equal to 1/2. Really, things don't get too interesting until I calculate C2. To calculate C2, I want to take the second derivative of my function evaluated at 0, so negative 1/4 in this case, and then divide that by 2 factorial. 2 factorial is 2 times 1, in other words, 2. So I get negative 1/4 divided by 2. Negative 1/4 divided by 2 over 1. If you multiply by the reciprocal of the denominator, you'll get negative 1/8. Finally, to figure out C3, I take the third derivative of my function evaluated at 0, which is equal to positive 1/4, and I divide that by 3 factorial. 3 factorial is 3 times 2 times 1, in other words, 6. So I have 1/4 divided by 6, which is equal to 1/24. Now that I have the four coefficients, I know my third degree Taylor polynomial. T3 of x would just be equal to 1/24 x cubed minus 1/8 x squared plus 1/2 x plus the natural log of 2. The third degree polynomial that best fits the function f of x equals the natural log of x plus 2 is this third degree Taylor polynomial, which you can calculate pretty quickly if you have these formulas. And the nice thing about these formulas is they're pretty intuitive. You can see where they all come from following the logic of the previous videos. But even if you don't care where they come from, they're pretty easy to memorize, right? C3 is the third derivative evaluated at 0 divided by 3 factorial. If you really wanted to encapsulate all this information, we could say that T3 of x is always equal to this polynomial right here. Because my third degree Taylor polynomial is C0 plus C1 times x plus C2 times x squared plus C3 times x cubed. And C3, for example, is just the third derivative of my function evaluated at 0 divided by 3 factorial. So that goes right there. What we did already up above is we redid all the work to figure out the third degree polynomial when our function f of x was equal to the natural log of x plus 2. You might not be that impressed. You might not see the importance of a polynomial approximating a function, but trust me, it's super powerful, and we'll be able to see in the next couple of videos what's so cool about it. It really is one of the most interesting results in all of calculus. But before I try to impress you with how powerful it is, I want to give you a couple more examples to make sure that you can always come up with these polynomials on your own. Let's see if we can figure out the fourth degree Taylor polynomial for f of x equals the cosine of x. Well, the way I would think about this is I need to know C0, C1, C2, C3, and C4. Fortunately, I have formulas for each of those things. You can go back to the previous page and look at those formulas if you want, but maybe you don't even need to. Maybe they're intuitive enough and logical enough that you can just memorize them. F of 0 divided by 0 factorial. C1 would be f prime of 0 divided by 1 factorial. C2 would be f double prime of 0 divided by 2 factorial. C3 would be f triple prime of 0 divided by 3 factorial. And C4 would be f quadruple prime of 0, which is typically written with a 4 in parentheses, because if you write enough apostrophes, it's really hard to look at, of 0 divided by 4 factorial. Can we figure all these things out? Absolutely. What we'll need is the first derivative, the second derivative, the third derivative, and the fourth derivative of this function f of x. Fortunately, this function f of x is just cosine of x, and taking derivatives is really easy. The derivative of cosine is negative sine, so f prime of x is negative sine of x. The second derivative of cosine is the derivative of the derivative, so the derivative of negative sine. The derivative of sine of x is cosine of x, so the derivative of negative sine of x is negative cosine of x. The third derivative of cosine of x is the derivative of negative cosine of x. The derivative of cosine of x is negative sine, so I get negative sine, in other words, positive sine of x. The fourth derivative of this function is the derivative of sine. The derivative of sine is just cosine of x. And if I had to go any further, I'd kind of just see this repeating pattern, right? The fifth derivative would be the derivative of cosine, which we already figured out was negative sine. The sixth derivative would be the derivative of that fifth derivative, which would be the derivative of negative sine, which we already figured out was negative cosine, and so on. Anyways, we have our 4 derivatives here, but really these formulas don't involve the 4 derivatives evaluated at x. They involve the 4 derivatives evaluated at 0. So I need to know f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and f quadruple prime of 0. Probably harder to write than they even are to figure out. For f of 0, I think back to my unit circle. The cosine of 0 is equal to 1. For f prime of 0, I need to know the negative of the sine of 0, but the sine of 0 is just equal to 0, and the negative of 0 is just equal to 0. For the second derivative, I need to know the negative of cosine of 0. We already talked about the cosine of 0 being equal to 1, so the negative of the cosine of 0 would be negative 1. The third derivative, we're looking for sine of 0, which we already talked about being equal to 0. And the fourth derivative is just cosine of x. Cosine of x evaluated at 0, as we already figured out, is equal to 1. If I want to know the coefficients on my fourth degree Taylor polynomial, what I have to do for the constant term is take f of 0 and divide it by 0 factorial. F of 0 is 1, 0 factorial is 1, C0 will end up being equal to 1. What about C1? I want to take f prime of 0, which is 0, and divide that by 1 factorial, which is 1. 0 divided by 1 is equal to 0. What about C2? It's the second derivative evaluated at 0, which is negative 1, divided by 2 factorial. 2 factorial is 2, so I get negative 1/2. What about C3? Well, it's the third derivative evaluated at 0. The third derivative evaluated at 0 is 0, and 3 factorial is equal to 6. 0 divided by 6 is just equal to 0. And finally, C4 is the fourth derivative of this function evaluated at 0, which we know is equal to 1, divided by 4 factorial, which is 4 times 3 times 2 times 1. In other words, 4 times 3 factorial, so it's 24, 4 times 6. I got the coefficients for my fourth degree Taylor polynomial, so I know my fourth degree Taylor polynomial. T4 of x would be equal to 1/24 x to the fourth power plus 0x to the third power minus 1/2 x to the second power plus 0x to the first power plus 1. It's kind of shocking to me anyways that this graph looks anything like the graph of cosine of x. Because if you're picturing the graph of cosine of x in your head, you're picturing this kind of infinite oscillating wave. But remember, the idea is not for this polynomial to approximate this function everywhere. It's for this polynomial to approximate this function when x equals 0. And if we take a look at the graph of y equals cosine of x and y equals 1/24 x to the fourth minus 1/2 x squared plus 1, we'll see the expected result. Here's the graph of y equals cosine of x, this wave that oscillates between -1 and +1, and that does one full revolution in a distance of 2 pi. Pi is like 3.14, so 2 pi is a little bit more than 6. Here's one oscillation of the wave. Now if I take a look at y equals 1/24 x to the fourth minus 1/2 x squared plus 1, in other words, our fourth degree Taylor polynomial, we get this graph. That's kind of cool, right? The graph in blue very closely approximates the graph in red when my value of x is close to 0. Yeah, when you go way out to the side and we're not close to 0, it doesn't look that similar anymore, but that wasn't our goal. Our goal was to approximate the function in red with the polynomial in blue close to 0, and as we zoom in here, we can see that we did a really good job of doing that. One more example and then I'll end this video. Let's figure out another Taylor polynomial. This time it'll be a 5th degree Taylor polynomial, and you're like, wow, that's going to take forever. No, it won't, because the function we're going to use f of x is e to the x, and e to the x has some really nice properties. We know that the derivative of e to the x is just e to the x, so what that means is the first derivative, the second derivative, the third derivative, and so on are all equal to e to the x power. Remember, we don't want the first derivative, second derivative, third derivative, and so on evaluated at x. We want all those evaluated at 0. So we change all our x's into zeros. We get e to the 0 power, which is equal to 1. What I'm saying is for the function f of x equals e to the x, f of 0 is the exact same as f prime of 0, which is the same as f double prime of 0, f triple prime of 0, and so on, and they're all equal to 1. What does that mean? It means figuring out the coefficients for the Taylor polynomial will be really easy. Because remember, we have our formulas here for the coefficients of the Taylor polynomial. The constant term in the Taylor polynomial is always f of 0 divided by 0 factorial. F of 0 is just equal to 1. So we get 1 divided by 0 factorial, which is also equal to 1. C0 is just equal to 1. What about C1? Well, that's going to be f prime of 0 divided by 1 factorial. But f prime of 0, much like f of 0, is just equal to 1. So all we got to do is divide by 1 factorial. 1 factorial is 1. So C1 is also equal to 1. What about C2? Well, C2 involves the second derivative of my function evaluated at 0 divided by 2 factorial. But the second derivative evaluated at 0, just like the first derivative, just like the function, is equal to 1. So I get 1 divided by 2 factorial. 2 factorial is equal to 2. So I get 1/2 for C2. C3 isn't much harder. It's the third derivative of my function evaluated at 0 divided by 3 factorial. The third derivative, just like all the other derivatives evaluated at 0, is just equal to 1. So it's just 1 divided by 3 factorial. 3 factorial is equal to 6. 3 times 2 times 1. So I get 1/6. Two more coefficients that I need. C4 would be the fourth derivative of my function evaluated at 0 divided by 4 factorial. But the fourth derivative, as we know, evaluated at 0 is just equal to 1. So it's 1 over 4 factorial. 4 times 3 times 2 times 1, or 4 times 6, is 24. And then finally, C5, the last coefficient in my 5th degree Taylor polynomial, is the fifth derivative of this function, evaluated at 0, divided by, kind of low on room here, 5 factorial. The fifth derivative of this polynomial evaluated at 0 is just equal to 1, so it's 1 over 5 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1, which is just 5 times 4 factorial. So it's 5 times 24, so it's 120. I have all the different coefficients for my polynomial, so I can figure out T5 of x. It would be 1 divided by 120 times x to the 5th power, plus 1 divided by 24 times x to the 4th power, plus 1 divided by 6 times x to the 3rd power, plus 1 divided by 2, x squared, plus 1x plus 1. This polynomial is going to approximate the graph of y equals e to the x for values of x near 0. How good of a job does it do? Well, a pretty damn good job. Don't believe me? Let me show you Desmos. All right, let's take a look. Here's the graph of y equals e to the x, this familiar graph shown in red. Maybe I'll zoom out a little bit to show even more of this graph. Let's take a look at this polynomial. 1 over 120x to the fifth plus 1 24th x to the fourth plus 1 6th x cubed plus 1 half x squared plus x plus 1. Our fifth degree Taylor polynomial. We're expecting something that looks a lot like the graph in red, especially close to x equals 0 here. Let's take a look. Kind of cool, right? I mean, it's so close that you can't even see the graph in red when we're close to x equals 0 here. It approximates it almost exactly when we're near 0. Sure, when you get x values at like -5, it's nowhere close, but that's okay. That wasn't our goal. Our goal was to approximate this graph near x equals 0, and this polynomial does a great job of that. The idea for this video was to get you comfortable calculating Taylor polynomials for any function efficiently. Not with the intuitive goal that we had in the last video, but with the more formulaic goal of this video. In the next video, we'll go back and we'll kind of talk about why we care so much about Taylor polynomials and some cool results that we can find from them.